All right, I think we're live here. Um, Go ahead and submit some comments. Let me know that we exist in YouTube land. Say hello. Anybody out there? Looks like we're live. Somebody send a comment. Let me know that we're alive. Any comments yet?
Yep. Permeet says, hey, Polly. Nick Ross says, look, it's all good, Polly.
Okay, so thanks for coming back in today and rejoining us for this live broadcast. Today we're going to talk about Lyft. Experimenting with some new things you see down here in this corner over here. I was able to embed PowerPoint and OBS. So I guess as time goes on and I figure out new ways to use the software, I can maybe do some more entertaining things for you guys to get my point across. Anyway, the other thing, it's going to take me time to get used to talking to a video camera with my executive producer and assistants in the background laughing at me. Anyway, so I'll get started here. I've got it connected to PowerPoint, and let's see, there we go. So to recap from the last discussion when we talked about the 4 forces of flight, which are really the 5 forces of flight. If you just do a random search on the internet of the forces of flight, you get this comes up. It's a smattering of different drawings if you click on the images, and I so disagree with it. I wish I could go and change every single one of those images because they're just not right. And why not just draw it right the first time? And let me click. Why not just draw it right the first time with lift, weight, thrust, drag, and balancing tail load as they would be shown appropriately? I think this is the way right here that you see. That's the way that every picture describing the forces of flight should be drawn. And again, I'd argue an aerospace engineer, scientist, aeronautics engineer that, and I'll throw this challenge out to you guys. If you guys can, design and fly an airplane, send me a little video clip of an airplane flying without a tail or without a balancing tail load. If you guys can make an airplane fly without a tail, without a balancing tail load, I'd be interested to see it. Anyway, something else just to answer some questions that came up in the comments last time. Somebody asked about lift and what that total force vector of lift represents. The total force of lift is equal to the weight of the airplane plus the balancing tail load. So if you take, like in that drawing right here, if you take the weight of the airplane and the balancing tail load, those vectors, and you sum them up, and let's say the weight of the airplane is 1,000 pounds, and then let's say the balancing tail load to maintain a level flight attitude is, let's just say for instance, it's 200 pounds. So total lift would be the 1,000 pounds, the weight of the airplane, plus the 200 pounds. So total lift would actually be 1,200 pounds. Another little demonstration I'll do here with how the balancing tail load works is, again, I got my little flight test chuck glider here. So here we go. Right now, this string up top here is representing lift. This string right here is going to represent weight. And as you can see, I have them offset. We have lift here, we have weight here, because our center of gravity on this airplane is actually right about where this string is. Our center of lift is going to be, I know this is a delta-shaped wing, but if you were to sum up all the forces, all the lift force on this wing or on this airplane, it would be roughly right about here. So, as you can see right now, I have not put any balancing tail load in. If I put balancing tail load in, now this airplane flies. Without it, the airplane just does a lawn dart. Now, how we control the balancing tail load is we as pilots controlling the airplane, we have a control column in the front of the airplane that allows us to pitch the airplane either up or down. When we pitch up, we pull back on the yoke, or in the RC airplane world, we pull back on our stick, and we apply the elevators here, bend, and create more of a balancing, more of a tail down force, which pitches the nose of the airplane up. As we push forward or release pressure and push forward, the nose of the airplane goes down. So that's all we're doing. There's never a negative balancing tail load. If there was a negative balancing tail load, this airplane would just do tumbles. So as you can see here, I can control the airplane just by adjusting the balancing tail load. So anyway, just wanted to show you guys a visual representation of that, which you can see here. Somebody please draw up an airplane that is capable of flight without a balancing tail load, and I'll be pretty impressed. Anyway, that's that. We're going to next. Let me click my PowerPoint here. History of flight. All right, I'm gonna play a little video. Some of the kids that I've worked with in the past have already seen this video. I'll get this video started. I'm gonna mute my main speaker and just leave in the comments section if you guys don't hear any volume, and I'll get my text on it right away.
Well, I started out down a dirty road. Started out all alone, and the sun went down as I crossed the hill, and the town lit up. The world got still. I'm learning to fly, but I ain't got wings. Coming down is the hardest thing. Well, the good old days may not return, and the rocks might melt, and the seed may burn. I'm learning to fly, but I ain't got wings. Coming down is the hardest thing. Some say life will beat you down, break your heart, steal your crown. So I've started out for God knows where. I guess I'll know when I get there. I'm learning to fly around the clouds,
All right, guys, I'm back. Let me get this screen made smaller. Wrong one. All right. In that video, so you guys, I think you all can hear me. My audio is saying that you can hear me. In the video, this kind of lead up to talking about lift today. All those people that pushed aviation to the next level, aeronautics to the next level, what do you think are some of the common traits that they had? What did they have in common? You guys can leave it in the comment section, like what made them successful? How did they become successful? So to keep this interactive, because that's how I do these lectures, these conversations, I guess. I don't want to be me lecturing you. I'd rather have it be a feedback where you guys give me comments and we move on. Anyway, give me some comments. What did those inventors, those scientists, what did they all have in common? What enabled them to succeed? I'll give you a second to leave some comments.
30-second delay.
All right, so how about what you guys come up with? Get my mouse going here. How about the following? A dream, a vision, desire, motivation, passion of what they were doing. Do you think they listened to the naysayers when people said, no, you're never going to make an airplane fly, you're never going to make an unmanned air vehicle fly, you're never going to have powered manned flight? Do you think they listened to the naysayers? Do you think they gave up after the first or second attempt? They focused on a way to be successful. They learned from their mistakes. And they were not afraid to pursue their dreams. So they kept pursuing, kept working hard. Now, in the history of flight, there's only been one human being to ever accomplish flight. And that human being would be the one, the only Michael Jordan, Air Jordan, his airness. Anyway, moving on. Aerodynamic lift. It's the force that enables the airplane to achieve flight. What does it take to generate lift? How do we generate lift? So I'll give you a couple seconds here to come up, send it in your comments section. What does it take to produce lift? And I want to try to drag this out of you just like I do in a live lecture. What does it take to produce lift? So I'll give you guys a couple seconds to think about it, and then we're going to answer that question.
Kermit did chime in. They believed in themselves.
All right, I think I gave you guys enough time. Keep leaving in the comments section here. What does it take to produce lift? I know there's a couple of my students that have seen this lecture in the past. They're listening right now, I'm sure. I hope they got the comments right. Anyway, join in if you want. What I'm going to write up here is the equation for lift. Lift equals coefficient of lift times 1/2 rho v squared s. Now, I know for the younger kids that might be watching or listening to this, don't worry, we're not going to do any math here today. We're going to keep this all non-math based. Stick with me here, you'll see where this is going. So, what do we need to produce lift? First of all, we need something to produce lift with. We need a body, we need a ball, we need We need a wing, we need a surface, we need something to interact with the airflow. So a wing is a way to interact with airflow. If I throw this pen, it will interact with the airflow and it will produce some lift. So first thing we need is we need something to create lift with. That's what S is in this equation. S equals a surface area. So meaning we just need an object. It can be any object. I can take the Bun Bun, my executive assistant over here. I can take the Bun Bun, I can pick him up and throw him across the garage where we're recording from. He will produce some amount of lift. Not very good, but he will produce some lift. So I need a body. Second thing we need this right here, 1/2 rho. You say, what the heck is that, Mr. Kelp? 1/2 rho is simply we need a medium, a fluid, for that vehicle to interact with. So we need air, or we need a fluid, as we would call it in fluid mechanics. In space, there is no air. It's a vacuum. There are no air molecules. Well, there are, but they're just very, very, very far spread apart. A wing does not produce any lift in space. In space, you're in a constant state of free fall. Here on the Earth, we have an atmosphere. And let me click forward one more slide. Here. There's the lift equation. There's what I was talking about, atmosphere. So if you look down here, you notice on the surface of the Earth, those air molecules are more compacted. As we go higher and higher and higher in altitude, those air molecules get more and more spread apart. So once we get up here, this 100,000 feet, 200,000 foot range, those air molecules are now more and more farther apart from each other. And then, like I said, once we get out to space, they're really spread apart. There's actually some really cool YouTube videos that explain how far away particles are, or molecules are in space. Anyway, so we need air density, which is 1/2 rho. So down here on the surface of the Earth, think of us being in the ball pit that you played in as a kid. All those air molecules are compact around us. Though those air molecules being compacted and tight together, those allow our wing or our airplane something to interact with. So that's what rho is. Rho is just air fluid or air density. I think that all got on the screen there. Yep, air density. All right, so the next thing we need, v squared, which is velocity. We need to give the object velocity. So I've got my chuck glider here again. If I don't throw my chuck glider and it'll fall. It'll free fall back to Earth because there's no velocity here to cause lift to react. Now if I give it a chuck, or if I put a motor on this and power up the motor, then we have now we have a way to give ourselves velocity. So that's why airplanes have motors on them. You can say, but Mr. Kelp, glider doesn't have a motor on it. Well, a glider doesn't have a motor on it because it can use the thermals that come off the Earth and wind, local area winds, to become airborne. And they use that wind or the thermals as that lifting force to create velocity. So we got surface area, 1/2 rho, which is air density, v squared, which is velocity, and then we got CL, which is simply coefficient of lift. Coefficient of lift, that's step aside here. Coefficient of lift, what coefficient of lift is every body has a capability to lift, some better than others. So if I throw my glider, it's going to glide for a distance. It's going to have a very low coefficient of lift. if I take this eraser and I chuck this eraser across the room, it's not going to go as far as this glider. The coefficient of lift for this eraser is much lower than the coefficient of lift for this glider. So the better the coefficient of lift, the better at flying. Remember earlier I said I could take my executive assistant over here, Bun Bun, I could pick him up and chuck him across the room. His coefficient of lift would be almost next to zero because he's not a very good lifting surface. Anyway, let's see here. What else I gotta go and talk about? Air density. All right, so next up, I want to keep these videos short, quick, just 10-15 minute videos so I don't bore people to death and do hour-long lectures up here, discussions. Next up, we're going to talk about the theories that support lift. So those would be Bernoulli's principle, Coanda effect, and Sir Isaac Newton and his laws and how they affect lift. In the comments, I said that this would be the controversial lecture. It's the next lecture that's controversial because there's so much disagreement on the different theories and how they apply to lift development. So I'll give you my best explanation. May not be perfect, but even in the professional world of aeronautics and aerospace, people get into disagreements all the time about the theories of lift. Anyway, we'll keep doing these videos. As long as you guys are enjoying them and I enjoy doing this, I'll keep doing these videos. Some of you might ask, why are you doing these videos, Mr. Kaup? And simply, I enjoy doing them just to share my passion for aviation, aeronautics, and aerospace. So that's why I do this, and I hope it helps some of the viewers out with understanding aerodynamics and aeronautics, and then for the kids that go off and become interested in aviation, specifically those that want to go off and fly UAV, UAS, or those who want to go off and do a professional pilot career. I hope I can help you with these videos as well. One of these days I'll cut a video here in the future about career paths in aviation or in aerospace as well. Anyway, before I sign out today, anybody got any questions? If you've got any questions, go ahead and submit them in the comments section. Do we have any comments? Any questions?
Not yet, but there's a delay.
There's a little delay, so I think it's around a 20-second delay or so. So we'll wait for the questions to pop up here. All right, do we have any questions? Any comments? All right, well, if you do have any comments or questions, put them in the comments section, or if you found out about this post on Facebook, you can put a comment in one of the Facebook posts, and then I will answer that question next time. Anyway, guys, thanks for tuning in today. We'll see y'all next time. There was a question.